Before July of 2025, astronomers thought they had the universe under control. We had models, predictions, decades of carefully tested theories, and the confidence that whatever arrived from the depths of space, we could categorize it, measure it, and move on. But then something appeared that shattered that certainty. A faint smear of light against the starfield, spotted by a survey telescope in Chile, became the beginning of a story that has left the world's smartest scientists stunned and searching for answers. They named it 3IATLAS, the third confirmed interstellar visitor to ever pass through our solar system. But that simple label doesn't capture the chaos it unleashed in astronomy, because the more telescopes turned toward it, the more it defied everything we thought we understood. Imagine a rock no larger than a small city, traveling faster than any comet or asteroid ever recorded, nearly 130,000 miles per hour. That alone should have made it remarkable. But speed was just the opening act. Within days of its discovery, astronomers noticed something they didn't expect. Atlas wasn't inert. It was alive with activity, shedding gas and dust like a living, breathing thing, a frozen relic from another star system, dormant for millions of years, suddenly awakened by the heat of our sun. For scientists, it was like watching a ghost come to life. And then came the details that made less and less sense. Its chemistry didn't match any known comet. Its gas cloud stretched farther than Earth's orbit around the sun, and its trajectory seemed almost too perfectly designed to pass through our solar system in plain sight. What started as a simple discovery quickly spiraled into one of the greatest astronomical puzzles of our time. Was 3IATLAS just an unusually strange comet? Or was it something entirely new, a type of interstellar wanderer we've never even imagined? The truth might change how we see not just our solar system but the galaxy itself. It all started on July 1st, 2025, a date that would go down in history as the day astronomy's foundations were shaken. It began as a routine scan, another night under the stars where a telescope on the Atlas survey station in Chile would sift through the darkness, looking for any potentially hazardous objects heading toward our solar system. The station's automated systems were trained to spot asteroids, comets, and any other debris that might one day be a threat to Earth. But this time, something unusual appeared in the sky. At first glance, it looked like any other faint streak of light against the vast backdrop of stars. Just another moving dot in the dark expanse. The object was 4.5 astronomical units away from the Sun, far beyond the orbits of Mars and Earth, sitting comfortably within the outer solar system's cold, quiet region. Nothing that unusual there, at least not at first. But then the calculations came through. The numbers didn't add up. They didn't fit the patterns we'd seen with other objects before. This wasn't just a comet or asteroid making its way through our neck of the woods. This was something far stranger. The object's trajectory, a hyperbolic orbit, immediately raised alarms. In the language of orbital mechanics, this meant one thing. This object was unbound. It wasn't trapped by the sun's gravity. It would never return to our solar system again. What we were looking at wasn't just another object from the outer solar system, but a traveler from another star system entirely. 3IATLAS was officially born, and the astronomical community immediately realized this was something extraordinary. The significance of the object's unbound status was not lost on the scientists who examined it. Most of the objects we observe within our solar system, from the asteroids in the belt between Mars and Jupiter to the far-flung comets of the Oort cloud, follow predictable, elliptical orbits. They're part of our solar system's family, trapped in the sun's gravitational embrace. But 3IATLAS was different. It was a cosmic outsider, a visitor that had wandered the vast emptiness between the stars, never tethered to any one system. It had come from somewhere beyond our solar system, from the cold, dark void of interstellar space, a place that our best telescopes had barely begun to explore. As the object's trajectory became clearer, it was quickly determined that its speed was mind-boggling. It was traveling at over 130,000 miles per hour, more than 170 times the speed of a bullet. To put that in perspective, that's 29,000 kilometers per hour, the fastest interstellar visitor ever recorded. And while we might think of space as a place of stillness, filled with vast distances that take light years to traverse, Atlas showed us just how fast objects could move across it. This was no ordinary rock or ice fragment. This was a messenger from another star system, carrying with it secrets and mysteries that could change everything we thought we knew about the cosmos. In the days following its discovery, the world's most advanced telescopes turned their attention to 3IATLAS, racing against time to learn as much as possible about the object before it passed beyond our reach. The Gemini North Telescope in Hawaii, with its 8-meter mirror, trained its eye on the object, and what they found was truly perplexing. Surrounding the nucleus of 3IATLAS was a coma, a cloud of gas and dust being actively released as the sun's warmth began to heat the object. But this wasn't just any coma. It wasn't like the wispy trails of gas we typically see from comets in our solar system. This was far more compact, yet it was growing larger by the day. This wasn't the first time an interstellar object had been spotted. Oumuamua in 2017 and Borisov in 2019 had both made headlines as the first confirmed interstellar visitors to our solar system. But 3IATLAS was different. Unlike Oumuamua, which had passed through without showing any signs of gas release or activity, Atlas was alive. It was ejecting vapor into space, breathing in the sunlight after millions of years of dormancy. Its coma wasn't just a dust cloud, it was evidence of something far more complex, more active. But how was this possible? Comets from our own solar system, when they enter the inner solar system and are heated by the sun, typically start to sublimate their ices, transforming directly from solid to gas. That's what causes the famous tails of comets, visible from Earth. But for an object that had been traveling through interstellar space for millions of years, exposed to radiation and temperatures just above absolute zero, how could it suddenly start releasing gas? How had it survived the harsh conditions of space, and what triggered it to awaken now? These questions left scientists reeling. Atlas was defying everything they thought they knew about comets and space objects. They knew that interstellar objects could be strange. After all, the conditions between stars are vastly different from those around our sun. But nothing had prepared them for what Atlas was revealing. Every observation raised more questions than answers. There were no answers to explain how it had survived, no models that could account for its behavior, and no simple explanation for its chemical makeup. As astronomers continued to observe Atlas, they were struck by another unsettling fact. The object's trajectory as it passed through the solar system appeared to be almost too perfect. It wasn't just skimming through the solar system, making a quick pass between Earth and Mars. It seemed to be threading the needle between planetary orbits, in a path that suggested a level of precision that felt unnatural. The geometry of its path seemed so calculated, so deliberate, that it almost felt as though the universe itself had arranged for this moment. The closest approach to Earth would be 1.8 astronomical units away, roughly 270 million kilometers, and scientists quickly realized that this was an ideal opportunity to study an object from another star system up close, to examine its composition, its behavior, and to search for clues about its origins. But even as the best telescopes on Earth trained their eyes on Atlas, one thing became clear: this was no ordinary comet. This was something far more complex, far more mysterious. With every observation, the more the object revealed its strange and alien qualities. As the days passed, it became evident that Atlas was a unique and unprecedented visitor, one that would force astronomers to rethink their understanding of the cosmos. There were no clear answers, only more questions. It wasn't just passing through our solar system, it was challenging everything we thought we knew about the universe. And just when it seemed like things couldn't get more perplexing, Atlas revealed something even more mysterious. As the object drew closer to the sun, its coma grew, but so did something else, something that until then had been missing from earlier observations: a faint tail stretching away from the sun, forming behind the object. It wasn't like the brilliant tails we associate with comets in our solar system, which stretch out like long glowing streaks of light. This tail was subtle, nearly invisible in the faint light of space, but it was there, and it was real. The faint tail, which was finally confirmed by observations from the Gemini South Telescope, was a clear sign that Atlas was indeed undergoing processes similar to a comet from our own solar system. But again, it was different. The tail didn't behave like any comet we had ever studied before. And yet, even as this remarkable discovery was being made, one thing remained certain: the more scientists learned about 3IATLAS, the more they realized that this was a cosmic enigma. Atlas was not just an interstellar visitor, it was an object from a distant corner of the universe, carrying with it secrets we had yet to unlock. And for the briefest of moments, it had crossed into our solar system, offering us a glimpse into a world far beyond our own, and perhaps revealing a deeper truth about the nature of the universe itself. As the weeks passed and astronomers continued their observations, something even more remarkable became clear. The path of 3IATLAS through our solar system was nothing short of a cosmic spectacle. Imagine for a moment the solar system as a vast mechanical clock, its planets and orbits marked by the rhythmic ticking of celestial motion. Now picture a bullet, one fired from a distant galaxy, streaking through this cosmic machinery, threading its way with precise calculated movements between the gears of our planetary system. That bullet was 3IATLAS, and its trajectory through our neighborhood read like a masterful choreography, orchestrated by forces beyond our comprehension. The trajectory was a stunning reminder that space, though vast and empty, is anything but random. The speed of Atlas was staggering. As we've already established, it was moving at an unimaginable 30,000 miles per hour, or 209,000 kilometers per hour. But the real mystery lay in how it was moving. This wasn't some chaotic wanderer tumbling through space. No, this was a calculated path, a cosmic tour designed to take it through our solar system with an almost eerie precision. Its closest approach to the Sun, known as perihelion, would occur on October 29, 2025. But what made this moment so fascinating wasn't just the closeness of its pass, it was the position of the Earth. For nearly 2 months, from late September through early November, Earth would be positioned on the exact opposite side of the Sun, hidden from the view of telescopes. During this time, when 3IATLAS was at its closest point to the Sun, Earth's astronomers would be completely blind to the object. It was as if the universe itself had conspired to hide this extraordinary moment of cosmic activity, blocking our view just when we needed it most. The irony was palpable. Scientists had a limited window to study the visitor, and now, as Atlas was about to reach its most active point, it would disappear behind the Sun's glaring light, invisible to every telescope on Earth. This blackout period, as it's known in astronomy, was one of the cruelest twists in this cosmic story. Here was an interstellar object, racing toward the Sun, reaching its peak activity, and yet humanity would miss it, at least from Earth's perspective. This time of invisibility would span nearly 2 months, and when the object finally emerged in December, it would be so faint and distant that even the most powerful telescopes would struggle to track it. It was as if the universe was deliberately making this encounter more difficult, offering only fleeting glimpses of a cosmic mystery before it vanished into the void once more. But even in the face of these astronomical limitations, the precise geometry of Atlas's path offered something tantalizing, an opportunity to observe the visitor from another perspective. For astronomers stationed on Mars, 3IATLAS would present a rare chance for a unique view of the interstellar wanderer. As the object passed Mars on October 3, 2025, it would come within a mere 29 million kilometers of the red planet. That's closer than Mars's own moons come to the planet, offering an unprecedented opportunity for Mars-based telescopes to capture the visitor in all its cosmic glory. For the fleet of robotic explorers orbiting Mars, including the powerful Mars Reconnaissance Orbiter with its high-resolution camera, this would be an exceptional moment. These telescopes would be able to observe the object with far greater clarity than Earth-based observatories, which would be blinded by the Sun. Mars would serve as a cosmic vantage point, offering scientists a chance to study 3IATLAS during its closest encounter with another planet. It was a chance no one had expected, and one that could provide valuable insights into the behavior of this mysterious visitor as it passed through our solar system. But even with this rare opportunity, the situation was still far from ideal. As Atlas continued its journey through the solar system, it would be racing away from the Sun at over 150,000 miles per hour, 240,000 kilometers per hour, fading into the distance. By the time it reappeared in December, it would be so far out of range that amateur astronomers hoping to glimpse this interstellar wonder would find it nearly impossible. Despite the excitement of its discovery, 3IATLAS would remain an elusive ghost, fading into the depths of space faster than we could track it. As it reached its closest approach to the Sun, the implications of its path were becoming clearer. The geometry of its journey, the perfect alignment of its movements, was almost too precise to be a coincidence. What was going on here? Was 3IATLAS simply following the natural laws of orbital mechanics? Or was there something else at play? Its trajectory suggested an almost deliberate, carefully timed path. A path that led some to wonder whether this interstellar visitor was somehow following a cosmic route designed for our observation. Was this just an extraordinary fluke? Or could there be something more to the way this object was moving through the solar system? While scientists could only speculate on the exact reasons behind the object's path, one thing became clear. 3IATLAS was challenging everything we thought we knew about the universe. Here was an object, traveling faster than anything we had ever seen, following a trajectory that seemed both too perfect and too impossible to ignore. Its closest approach to Earth, on October 3rd, would be too far to detect with the naked eye, but the opportunity to study it from Mars would still be a monumental achievement. This cosmic traveler was now threading its way through our solar system, and the more we observed, the more it became apparent that it was like no other object we had ever encountered. The journey of 3IATLAS through our solar system is a tale of timing, precision, and astronomical opportunity. It's a reminder that the universe isn't just an empty expanse, but a vast, intricate system where even the smallest of objects can pass through with an elegance that defies our understanding. In the coming months, the race to observe this interstellar visitor would reach a fever pitch, as scientists around the world tried to gather as much data as possible before it disappeared for good. Every new observation added another layer to the mystery, another clue that could help unlock the secrets of this interstellar wanderer. But time was running out, and the window to study 3IATLAS was closing fast. In December, when the object reappeared, it would present one final opportunity to uncover the truth behind its journey. By then, however, it would be so far from the sun, so faint in the sky, that tracking it would become increasingly difficult. The final chance to understand 3IATLAS would come and go in the blink of an eye, and by then it would be lost once more to the cold, dark expanse of interstellar space. For astronomers, this would be a bittersweet moment. They had witnessed something extraordinary, a rare glimpse into the vast unknown universe, but they knew that, like so many mysteries of the cosmos, the truth of 3IATLAS might slip away forever, leaving behind only questions and a sense of wonder about what else lies beyond our reach. As the cosmic curiosity of 3IATLAS continued to unfold, astronomers began to realize that the object was proving to be even more mysterious than they had initially anticipated. What was first thought to be a fleeting comet from another star system had now become something far more complex, an object that wasn't merely passing through our solar system but was challenging the very laws of celestial mechanics and physics we had come to trust. On July 21, 2025, the Hubble Space Telescope, one of the most advanced observatories humanity had ever launched into space, trained its powerful eye on 3IATLAS. The images that emerged from Hubble's digital sensors were nothing short of a paradox. The object's appearance was both alien and familiar, a teardrop-shaped cloud of dust and gas, glowing faintly against the backdrop of the infinite black. Yet the object's form wasn't quite right. It seemed to be caught in the process of something much larger than itself. Its nucleus, a solid, enigmatic core, shrouded in its own veil of gas. Hubble's stunning optics, capable of resolving distant objects with unparalleled precision, showed astronomers something extraordinary. They could see that the nucleus of 3IATLAS, its solid heart, was far smaller than expected. It appeared as nothing more than a point source buried beneath a veil of vapor, an object wrapped in its own shroud of activity. The initial observations revealed that the nucleus of 3IATLAS was likely no more than 3.5 meters across, a tiny fragment of a larger hidden object. For comparison, that's smaller than most cities on Earth. Yet, despite its small size, this seemingly insignificant piece of space debris was producing an enormous cloud of gas and dust. The coma, the dust and gas surrounding the nucleus, stretched thousands of kilometers in every direction, far larger than any comet we had ever studied before. It wasn't just any cloud, it was a massive structure with strange, almost inexplicable qualities. What made it even more perplexing was that the coma was not symmetrical, as one would expect from a typical comet. Instead, it had an unusual, almost unnatural shape. It was teardrop-shaped, stretched out in a direction that hinted at complex dynamics taking place within the object itself. The coma, scientists realized, was being sculpted by forces far beyond simple outgassing from the nucleus. The shape suggested that some unknown physical process was at play, creating this distortion in the gas cloud. But perhaps the most striking and puzzling feature of the Hubble images was the tail, or rather the lack of one. Comets, as we know them, often display long, visible tails that stretch out behind them as gas and dust are pushed away by solar radiation pressure. The tail of 3IATLAS, however, was nothing like the long, glowing streaks we were accustomed to seeing in comets that have ventured into the inner solar system. At first, Hubble's images suggested the tail was barely visible. It was faint, almost hidden, a subtle trace of a comet's most defining feature. Initially, astronomers couldn't even confirm it. They could see hints of a tail, but nothing concrete. nothing that fit the models they had used for centuries to describe how comets behave. Then came the observations from the Gemini South Telescope, stationed in Chile, which provided a clearer view of 3I-ATLAS and its tail. By late August, the faint, almost imperceptible trail of dust and gas that Hubble had struggled to reveal finally came into sharper focus. The tail was there, but it was subtle, almost ghostly in appearance. It wasn't the brilliant, radiant tail of a classic comet, flaring out in a spectacular display. Instead, it was a faint, wispy feature, barely visible against the surrounding stars, extending away from the sun with delicate precision. It wasn't what scientists had expected, but it was there, a tail that defied conventional wisdom about how comets should behave. What made this discovery even more bewildering was the size of the tail in relation to the nucleus. The nucleus of 3I-ATLAS, as we've already discussed, was incredibly small, just a few kilometers across. Yet the tail extended far beyond the nucleus, growing larger as the object neared the sun. In some ways, it was as if the tail was operating on a scale that didn't match the size of the object itself. This mismatch between the size of the nucleus and the scale of the tail added another layer to the mystery. How could such a small object produce such an enormous gas cloud? Where was all the material coming from, and how was it being expelled into space with such precision? The more scientists looked, the more they realized that 3I-ATLAS was playing by its own rules, throwing out every model of comet behavior they had developed. As the weeks passed and 3I-ATLAS continued its approach to the sun, astronomers were faced with more questions than answers. Despite all the sophisticated technology and advanced instruments being used to study the object, it was still shrouded in mystery. The tail, which should have been one of the most visible features of the object, was frustratingly elusive. It wasn't behaving like any comet they had ever encountered. The standard theory of solar radiation pressure pushing dust and gas away from a comet's nucleus didn't seem to explain the faintness and unusual geometry of the tail. Some astronomers speculated that perhaps the dust grains in the tail were unusually large, making them more resistant to radiation pressure and causing them to behave differently. Others proposed that the tail was being shaped by some form of interaction with the solar wind, which was amplifying the effects of outgassing and creating a more subtle tail. But these ideas remained unproven, leaving the tail of 3I-ATLAS as one of the most baffling features of this interstellar visit. The mystery didn't end with the tail. Observations from the James Webb Space Telescope and other instruments started to reveal something even more perplexing: the chemical makeup of 3I-ATLAS. Most comets in our solar system, when studied closely, show a clear and predictable chemical signature. Water vapor is usually the dominant component, with smaller amounts of other volatile compounds such as carbon dioxide and ammonia. But when Webb's infrared sensors examined the spectrum of 3I-ATLAS, they detected something unexpected. The object's chemical signature was dominated by carbon dioxide, a far cry from the usual water-dominated composition of comets in our solar system. The carbon dioxide to water ratio was off the charts, with a ratio of 8:1. This was extraordinary. In fact, it was so extreme that no comet in our solar system had ever been observed with such a composition. This unexpected chemistry opened up a new set of questions. Why was 3I-ATLAS so different from other comets? What did its composition reveal about its origin? Some astronomers began to speculate that this chemical signature was a clue to the object's birthplace, that 3I-ATLAS may have formed in a star system with very different conditions from our own. In particular, it suggested that 3I-ATLAS might have originated from a region of its parent star system where carbon dioxide was more abundant than water, possibly near the carbon dioxide snowline, a region in a star system where temperatures are just right for carbon dioxide to condense into solid ice. The discovery of such a unique chemical signature raised even more questions. What other kinds of conditions might exist in the distant reaches of interstellar space? Could other interstellar objects like 3I-ATLAS carry chemical signatures that defy everything we thought we knew about planetary formation? As more data poured in, it became clear that 3I-ATLAS was not just another comet. It was something entirely new, something that could rewrite the textbooks on interstellar objects and planetary formation. Its strange appearance, its enigmatic tail, its bizarre chemistry, each discovery only deepened the mystery, leaving scientists scrambling to piece together the puzzle. What we were witnessing was not just the passage of a celestial object through our solar system, but the revelation of an entirely new chapter in the story of the universe. The more astronomers looked at 3I-ATLAS, the more they realized that its secrets were not easily unlocked. With every new observation, the object revealed something different, something unexpected, something that forced scientists to reconsider their assumptions about comets, interstellar objects, and the very nature of the cosmos. In the case of 3I-ATLAS, it seemed that the universe wasn't just presenting us with a visitor, it was challenging us, forcing us to confront the limits of our understanding and embrace the possibility that there is far more to learn about the universe than we ever imagined. The more astronomers delved into the heart of 3I-ATLAS, the more they were forced to confront an uncomfortable reality. Everything they thought they knew about comets, interstellar objects, and even planetary formation was being upended. One of the most shocking revelations came not from the object's strange appearance or its baffling trajectory, but from its chemistry. In the world of astronomy, the chemical makeup of a comet is often the key to unlocking its origins. It's like reading the fingerprints of a mysterious visitor, a piece of evidence that can reveal where it came from, how it was formed, and what kind of star system it once called home. But in the case of 3I-ATLAS, its chemistry didn't just raise questions, it shattered everything that scientists thought they understood about the building blocks of the universe. When astronomers first analyzed the spectral data from the James Webb Space Telescope on August 6, 2025, they discovered something truly perplexing. The carbon dioxide to water ratio of 3I-ATLAS was unlike anything they had ever seen. Most comets from our own solar system, when studied closely, exhibit a chemical signature dominated by water. In fact, water is usually the primary component in the gas released by these icy travelers. But 3I-ATLAS was different. Its spectral signature revealed a staggering 8:1 ratio of carbon dioxide to water. To put this into perspective, even the most carbon dioxide-poor comets in our solar system show a ratio of only 2:1, with water vastly outpacing carbon dioxide. But here was 3I-ATLAS, flaunting a composition that defied all expectations, raising the question, how could a comet from another star system have such an unusual chemical makeup? The discovery sent shockwaves through the astronomical community. How could an object from the cold, dark depths of interstellar space, which had traveled for millions of years through the vacuum of the galaxy, have this kind of chemistry? This wasn't just a small anomaly. This was a complete rethinking of the basic principles of cometary science. And as more data poured in, it became clear that the carbon dioxide-dominated composition of 3I-ATLAS wasn't an isolated phenomenon. It was a symptom of something much larger, something that had been hidden from us for centuries. The implications of this discovery were profound. For one, the extreme carbon dioxide to water ratio suggested that 3I-ATLAS had not formed in the same way as the comets in our solar system. Most comets we've studied, even those from the far reaches of the solar system, have formed from the icy building blocks of our solar nebula. These icy bodies are rich in water and other volatile compounds, which sublimate and form the familiar tails that make comets such spectacular sights in the night sky. But 3I-ATLAS wasn't from our solar system, and its chemistry suggested that it had formed in a very different environment, one where carbon dioxide was far more abundant than water. As scientists began to piece together the chemical puzzle of 3I-ATLAS, several potential explanations emerged. One of the most intriguing ideas was that 3I-ATLAS had formed near a carbon dioxide snowline in its parent star system. In any planetary system, there are specific regions where different volatile compounds freeze out of the gas phase and become solid ices. Water ice, for example, forms at colder temperatures in the outer reaches of a star system, while carbon dioxide has its own freezing point, somewhere in between the water snowline and the warm inner regions where rocky planets form. If 3I-ATLAS had originated in a region just inside the carbon dioxide snowline but outside the water snowline, it might explain the object's unusual composition. In such a region, the temperatures would have been just right for carbon dioxide to freeze out of the gas phase, while water remained in vapor form. This would create an object that was rich in carbon dioxide and poor in water, exactly the chemistry that 3I-ATLAS was showing. The discovery of a carbon dioxide-dominated comet raised even more tantalizing possibilities. If 3I-ATLAS formed in a zone like the carbon dioxide snowline, it might represent a completely different class of comet, one that forms in a star system with very different conditions from our own. The very fact that this object had traveled across the galaxy carrying this unique chemistry with it suggested that other star systems might harbor similar objects, with their own strange chemical signatures waiting to be discovered. 3I-ATLAS was a time capsule, offering us a glimpse into the chemical processes of another planetary system, one that was possibly billions of years older or younger than our own. It wasn't just a comet, it was a clue, a message from another star system, encoded in its gases and ice, waiting for us to decode it. But the carbon dioxide mystery didn't end there. Even as astronomers grappled with the implications of the extreme carbon dioxide to water ratio, new observations from NASA's FEX mission between August 8th and 12th added another layer of complexity to the story. FEX's infrared survey revealed something unexpected. The carbon dioxide emission from 3IATLAS wasn't confined to a small region around the nucleus. In fact, it extended outward for at least 38,000 kilometers, nearly 250,000 miles. This was the largest carbon dioxide coma ever mapped around any comet, far larger than anything seen in our own solar system. To put it in perspective, imagine the entire Earth-Moon system, and then stretch that distance by 50%. That's the scale of the carbon dioxide cloud surrounding 3IATLAS. It was so large that it made even the most dramatic cometary outgassing seem small by comparison. The sheer size of this emission region challenged our understanding of cometary physics. How could an object with a nucleus only a few kilometers across produce a cloud of gas that stretched over such vast distances? One of the theories proposed to explain this colossal emission was that 3IATLAS might be fragmenting, breaking apart and releasing chunks of carbon dioxide-rich ice into space as it moved through the solar system. If this were the case, the material being released would continue to sublimate, creating a massive carbon dioxide coma that extended far beyond the object itself. Another possibility was that the extended emission could be the result of interactions between the solar wind and a pre-existing gas cloud surrounding 3IATLAS, amplifying the apparent size of the emission region. Both explanations were speculative, but each one suggested that 3IATLAS was behaving in ways that defied the conventional understanding of cometary activity. This object wasn't just a piece of interstellar debris, it was an active, living entity, releasing gas and dust on a scale that had never been seen before. To make matters even more puzzling, further data from the SFOREX mission revealed even more strange behavior. The carbon dioxide cloud that surrounded 3IATLAS was unlike anything seen in other comets. It seemed to defy the normal rules of cometary outgassing, producing far more material than would be expected from an object of its size. In addition, the SFOREX observations showed absorption features at 1.5 and 2.1 micrometers, wavelengths that are consistent with the presence of water ice on the surface of the object, or in the near-surface layers. This raised even more questions. If 3IATLAS was indeed rich in carbon dioxide, then how could water ice still be present on its surface, albeit in such small quantities? Was the water ice trapped beneath an insulating layer of carbon dioxide, or was it being released in a manner we didn't yet understand? These new findings added yet another layer of mystery to the object. How could 3IATLAS be shedding carbon dioxide in such large quantities, while still harboring traces of water ice? The answer was elusive, but it suggested that the physical and chemical processes at play within 3IATLAS were far more complex than anything we had seen before. Perhaps this was an object that was still evolving, still reacting to the heat of the sun, in ways that we hadn't yet figured out. Its chemistry, its emissions, its very composition were all telling us that this object was like no other comet we had encountered. Not just a visitor from another star system, but a cosmic anomaly that was pushing the boundaries of what we thought was possible. And as astronomers continued to study the strange visitor, they were left with one undeniable truth. 3IATLAS was a game-changer. Its carbon dioxide dominance, its vast gas cloud, and its unexpected behavior were forcing scientists to rethink everything they knew about comets, interstellar objects, and the very processes of planetary formation. The universe had given us a gift, a glimpse into a star system unlike our own, a window into the unknown, and a reminder that the cosmos still has mysteries far beyond our understanding. As the months passed and astronomers continued their observations, one thing became overwhelmingly clear. The more they learned about 3IATLAS, the less they truly understood. Every observation, every new image or data point, raised more questions than answers, leaving scientists to grapple with the harsh reality that this interstellar visitor was not just an anomaly, it was an enigma that seemed to defy every model of celestial mechanics, cometary behavior, and planetary formation that had been built over decades of research. The more they studied it, the more they realized that 3IATLAS was not just a rare object. It was a cosmic puzzle that was testing the very limits of human knowledge. One of the most frustrating aspects of studying 3IATLAS was its size, or rather the uncertainty surrounding it. When astronomers first began to study the object, They were confident that they would be able to determine its size relatively quickly. After all, the size of a comet's nucleus is one of the most fundamental pieces of information that scientists can gather. Knowing the size of an object is key to understanding its composition, its behavior, and its potential for interacting with other celestial bodies. But in the case of 3I-ATLAS, things were far from straightforward. The Hubble Space Telescope had managed to capture some of the clearest images of 3I-ATLAS, and from these images, astronomers estimated that the object's nucleus was somewhere between 320 meters, and this is a massive range, from the size of a large building to that of a small city. How could this be? Was it that difficult to resolve such a seemingly simple question? The answer was surprisingly simple, yet deeply frustrating. The object's nucleus was shrouded in its own coma, a cloud of dust and gas, so thick that it obscured any clear view of the solid core. The coma was not just a faint halo around the nucleus, as one might expect with a typical comet. Instead, it was dense, dynamic, and actively shedding material into space. This made it nearly impossible for telescopes to resolve the true size of the object's nucleus, and so astronomers were left with little more than educated guesses. Some estimates put the nucleus at just a few hundred meters across, while others suggested it could be as large as 5.6 kilometers, a difference so vast that it seemed almost impossible to reconcile. Was 3I-ATLAS a tiny fragment of a larger body, or was it a more massive object, the size of a small asteroid? The uncertainty surrounding its size created a ripple effect throughout the entire scientific community. If they couldn't even pin down the object's size with certainty, how could they be sure about anything else? Its activity, its chemistry, its origin, everything hinged on understanding this one fundamental characteristic, and yet it remained elusive. Equally perplexing was the object's rotation state. Normally, when astronomers study small bodies like comets, they can track variations in brightness caused by the rotation of the object. These variations, known as light curves, provide valuable information about the object's shape, size, and rotation period. But 3I-ATLAS refused to cooperate. Despite the intense scrutiny from some of the world's most powerful telescopes, astronomers could not detect any periodic variations in its brightness. This meant they couldn't determine the object's spin rate, or even its rotation axis. Most small bodies in our solar system spin erratically, creating observable fluctuations in their brightness. But 3I-ATLAS appeared to be remarkably stable. Its brightness remained constant, showing no signs of the typical rotational variations that would be expected from an object of its size and type. This posed another huge puzzle. Why wasn't 3I-ATLAS behaving like other comets? Could it be rotating very slowly so that its rotation didn't produce noticeable changes in brightness? Was it perhaps tumbling in space in such a way that its surface features remained uniform from our point of view? Or more intriguingly, could 3I-ATLAS be completely different from any comet we had ever encountered? Some researchers even speculated that the object might be a single compact mass of material with no clear surface features, which would explain its lack of rotational fluctuation. This idea raised even more questions about the object's internal structure and the processes that were driving its activity. But it wasn't just the object's size and rotation that remained a mystery. The presence of water ice, or rather, the absence of it, continued to baffle scientists. Comets in our own solar system, when studied at close range, always show signs of water ice, which is one of the key components that drive their outgassing and the formation of their tails. Water ice sublimates under the heat of the sun, creating the characteristic coma and tail that are so familiar to us. But in the case of 3I-ATLAS, the water signature was shockingly faint. Early observations from the Swift Observatory had detected hydroxyl radicals, which are typically associated with water vapor being broken apart by solar ultraviolet radiation. This had led astronomers to believe that 3I-ATLAS might be releasing water vapor, just like any other comet. But as more data came in, the water story grew more complicated. Observations from SphereX showed a much weaker water signature than initially expected. In fact, the water signal was so faint that it led some researchers to question whether 3I-ATLAS contained significant amounts of water ice at all. Was the object simply too cold to release water vapor, or was something more complex at play? The faintness of the water signature created a dramatic contrast with the object's overwhelming carbon dioxide emissions, raising the possibility that 3I-ATLAS might be a comet unlike any other in the history of astronomy. Perhaps it wasn't releasing water at all, but instead was behaving in an entirely different way. The question of water and carbon dioxide was deeply connected to the object's outgassing behavior. If 3I-ATLAS was indeed emitting far more carbon dioxide than water, How was it generating such enormous gas clouds? Was it simply the result of sublimation, a process that involves the direct transformation of solid ice into gas? Or was something else at work? Some researchers speculated that 3I-ATLAS might be fragmenting, shedding large pieces of carbon dioxide-rich ice into space. Others suggested that the outgassing might be driven by solar-wind interactions with the gas clouds surrounding the object, amplifying the apparent size of the coma. These theories, while intriguing, remained unproven. No matter how many telescopes observed the object, no clear explanation emerged. 3I-ATLAS continued to defy explanation, leaving scientists grasping at straws as they sought to unravel its secrets. And then there was the tail, or rather the lack of a tail. As we discussed earlier, comets usually exhibit a clear anti-solar tail, created by the pressure of solar radiation pushing dust and gas away from the nucleus. But 3I-ATLAS's tail was different. It was faint, almost invisible, and astronomers couldn't figure out why. The object was shedding material at a rate comparable to other comets, but its tail remained elusive, a ghostly thread in the vast expanse of space. This raised even more questions about the object's activity. Was it ejecting material in a way that made the tail nearly invisible? Or was there something fundamentally different about the physics at play? At the end of the day, the central question remained, where did 3I-ATLAS come from? And what was its true nature? Despite all the sophisticated instruments and years of experience, astronomers were still left with more unanswered questions than they could count. The object's origins, its behavior, and its unique chemistry had led to an explosion of theories, but no definitive answers. What we were witnessing wasn't just the passage of an interstellar object through our solar system. We were witnessing the unraveling of our understanding of comets, interstellar debris, and the very forces that govern the behavior of celestial bodies. And as 3I-ATLAS continued its journey toward the outer reaches of our solar system, scientists were left to wonder, would we ever truly understand what we had just witnessed? Or would 3I-ATLAS remain a cosmic mystery forever? Despite months of observation and the deployment of some of the most advanced astronomical instruments in existence, 3I-ATLAS remained, in many ways, an enigma. The more scientists studied it, the more questions arose, and the deeper the mystery became. At the heart of the scientific community's frustration was the undeniable fact that, as the weeks went on, the things they knew about 3I-ATLAS only seemed to be a small fraction of what they still didn't understand. The gap between what was observable and what was comprehensible was growing, and it was clear that this interstellar visitor would not be easily understood. Take, for example, the question of its size. Astronomers had been able to measure the size of 3I-ATLAS's coma, the cloud of gas and dust surrounding the nucleus, with great precision. Yet when it came to the object's actual nucleus, the solid core, the uncertainty was almost maddening. As we've discussed, Hubble's imaging had constrained the nucleus size to somewhere between 320 meters and 5.6 kilometers in diameter, but that's a wide margin of error. The smaller end of the range would suggest that 3I-ATLAS was just a fragment, perhaps a piece of a much larger object, while the larger end would place it closer to the size of a small asteroid, a much more significant body. And this discrepancy didn't just raise concerns about the object's size, it hinted at something far more fundamental. Was 3I-ATLAS a coherent solid object, or was it a collection of smaller fragments, possibly held together by weak gravitational forces? The problem lay in the fact that the object's coma, the cloud of gas and dust surrounding it, was so thick and dense that it obscured any detailed view of the nucleus itself. While astronomers could see the outer edges of the coma with remarkable clarity, the nucleus remained hidden beneath a veil of gas. This forced scientists into a frustrating position. They couldn't definitively determine how big the object was, what it was made of, or even how it was structured internally. Every image captured by telescopes was like looking at a foggy window. It provided some insight, but not nearly enough to make a solid judgment. To make matters worse, the object's rotation state was just as mysterious. Typically, astronomers can measure the rotational speed of a comet by tracking variations in its brightness. As a comet spins, its surface area changes, causing the amount of sunlight reflected to vary periodically. These fluctuations, known as light curves, are one of the key ways scientists determine the rotation period of a small body like a comet. Yet 3I-ATLAS showed no such variations. It appeared to be unusually stable in terms of its brightness, with no detectable signs of rotational change. Was the object spinning incredibly slowly, too slowly to produce noticeable changes in brightness. Or perhaps it was rotating so uniformly that its surface was featureless, making it impossible to detect any variation. Some astronomers even suggested that the object might be tumbling through space in an unusual way, but the lack of brightness changes made this theory difficult to test. Without this vital information, scientists were left guessing. They couldn't determine how the object was moving or what forces were acting on it. In the absence of clear evidence, the question of 3I-Atlas's rotation remained unresolved, another frustrating layer to an already baffling puzzle. And then there was the matter of water, or more precisely, the absence of detectable water. Water ice is one of the defining characteristics of comets. As a comet approaches the Sun, the heat causes the water ice on its surface to sublimate, that is, to transition directly from a solid to a gas, creating the bright coma and tail that make comets so visible in the night sky. But in the case of 3I-Atlas, astronomers struggled to detect any significant amounts of water. Early observations from the Swift Observatory had suggested the presence of hydroxyl radicals, which are typically associated with water vapor being broken apart by solar radiation. This was initially taken as evidence of water sublimation, but the later observations told a different story. The data from SphereX and other instruments revealed that the water signal from 3I-Atlas was surprisingly weak. In fact, it was so faint that some researchers began to wonder if there was any water ice on the object at all. Could 3I-Atlas, unlike every other comet we've studied, be virtually devoid of water? And if so, what did that mean for our understanding of comets in general? The faintness of the water signal raised even more questions. If 3I-Atlas was expelling carbon dioxide in such large quantities, was it possible that water ice simply wasn't present? Or was the water trapped beneath a layer of carbon dioxide or other volatile materials? Perhaps there was an entirely new process at work on this comet, one that we had never seen before. But without clear evidence, the mystery only deepened. The tail, too, continued to elude simple explanation. As we've already discussed, 3I-Atlas's tail was remarkably faint, almost invisible to the naked eye. This was in stark contrast to the long, brilliant tails of most comets that we observe in our solar system. While comets typically produce tails of dust and gas that stretch for millions of kilometers, 3I-Atlas's tail was barely detectable, even with the most powerful telescopes. What caused this subtle behavior? Was it simply the result of a viewing angle that compressed the tail's appearance? Or was there something fundamentally different about the way 3I-Atlas released its gas and dust? Was the dust made up of larger particles that resisted radiation pressure? Or was there an entirely different dynamic at play? Some scientists speculated that the faint tail could be the result of an unusual interaction between the object's gas and the solar wind. The solar wind, a stream of charged particles emitted by the sun, can interact with the gas surrounding a comet, causing the material to spread out in a way that could make the tail less visible. But again, this theory was speculative. No matter how many observations were made, no one could pinpoint exactly what was happening to the tail. Was it just a matter of perspective? Or was 3I-Atlas somehow producing a tail in a way that no one had ever observed before? This was another major unanswered question, one that only added to the sense of mystery surrounding the object. Even more troubling was the question of 3I-Atlas's origin. While astronomers were confident that it was an interstellar object, meaning that it had originated from outside our solar system, the specifics of where it had come from and how it had been ejected from its parent system remained unknown. Some researchers speculated that the object had formed in the thick disk of our galaxy, an area populated by older stars and remnants from the early days of the universe. This theory suggested that 3I-Atlas could be as old as the galaxy itself, possibly even billions of years older than our Sun. Others proposed that the object had been ejected from a young, chaotic star system, where gravitational interactions with larger bodies had sent it hurtling through the galaxy. But despite these hypotheses, the precise origin of 3I-Atlas remained a mystery. Where had it come from? What star system had it been a part of? These questions, like so many others, were still unanswered. In the end, the mysteries of 3I-Atlas seemed almost too numerous to count. It was an object that defied every attempt to categorize it. Its size, its composition, its behavior, all of these aspects of the object were shrouded in uncertainty, leaving astronomers scrambling for explanations. Every new discovery raised more questions, and yet, despite all the data, the answers remained elusive. Was this the end of the thode for our understanding of 3I-Atlas? Or would further observations eventually unlock its secrets? No one knew for sure, but one thing was clear. 3IATLAS had forced the scientific community to confront the limits of its knowledge and to acknowledge that the universe still holds many more mysteries than we can fathom. As the mystery surrounding 3IATLAS continued to mount, scientists and astronomers were forced to confront a difficult reality. Traditional models of cometary behavior and interstellar objects were simply not enough to explain the strange nature of this cosmic visitor. 3IATLAS had defied expectations in nearly every possible way, from its unexpected carbon dioxide-rich composition to its oddly faint tail and irregular behavior. This wasn't just an ordinary comet making a flyby through our solar system. It was an object unlike anything that had been observed before, and as the weeks passed, the scientific community began to entertain increasingly bold and sometimes controversial theories about what 3IATLAS might truly be. One of the first questions that astronomers grappled with was the sheer size of 3IATLAS, or rather the uncertainty surrounding it. Was the object a tiny fragment of a much larger body, or was it a more substantial object on its own? Given the difficulty in resolving the nucleus through the dense coma of gas and dust, some scientists began to entertain the possibility that 3IATLAS was not a solid object at all, but rather a loose collection of fragments held together by weak gravitational forces. It could be a conglomerate of smaller objects, bound together by a diffuse gravitational field, acting more like a cloud than a single unified body. While such an idea seemed far-fetched, the lack of observable rotation and the strange behavior of the coma made it seem more plausible. This theory, if proven correct, could fundamentally alter our understanding of cometary bodies and the processes that govern their behavior in space. But the mystery of 3IATLAS's composition was far more profound than just its size. The discovery that the object's gas cloud was primarily composed of carbon dioxide, rather than the expected water vapor, caused a dramatic shift in the way scientists viewed interstellar comets. Theories about the object's chemical makeup began to diverge. One of the more conventional ideas was that 3IATLAS had formed in the outer reaches of a star system, possibly near the carbon dioxide snow line, where temperatures were just low enough for carbon dioxide to freeze into solid ice, while water remained in a gaseous state. If 3IATLAS had originated in such an environment, it could explain its unusual composition. But the question remained, why was it emitting such an extraordinary amount of carbon dioxide, and why was there so little water vapor? Could this object represent a completely new class of interstellar object, one that formed in a different kind of stellar environment from the comets we are familiar with? Some scientists speculated that 3IATLAS might have formed in a star system where conditions were vastly different from those of our own solar system. Perhaps its parent star was more massive or older, and its surrounding region contained higher concentrations of carbon dioxide and other volatiles that would not typically be present in our own solar system. This would suggest that 3IATLAS was carrying a chemical signature from a star system that was far older, or perhaps even one that had been subject to different stellar processes. If true, this theory could mean that 3IATLAS was not just an ordinary comet, but a relic from an entirely different galactic environment, offering a glimpse into a system that had undergone processes that our own solar system had not. But even more intriguing than these theories were, the more speculative, even controversial, ideas that began to emerge. Given the object's strange trajectory, its lack of detectable water vapor, and its highly unusual carbon dioxide signature, some researchers began to suggest that 3IATLAS could be something far more extraordinary than a simple comet. Could it be a probe, an artificial object perhaps intentionally sent to our solar system by an alien civilization? This hypothesis, while highly speculative and controversial, gained attention because of the sheer improbability of 3IATLAS's movements and features. The object's trajectory, for example, appeared almost too perfect. Its approach to the solar system seemed to be precisely timed, as if it had been deliberately directed in a way that allowed it to pass through the inner regions of the solar system, just within sight of Earth. The path was almost too calculated to be a mere random event in the vastness of space. While some astronomers dismissed this idea as far-fetched, others pointed out that the lack of water, the presence of unusual gases, and the faintness of the tail could all be signs that 3IATLAS was not behaving according to the natural processes we had come to expect from interstellar comets. Avi Loeb, a Harvard astronomer and prominent advocate for the search for extraterrestrial intelligence, was one of the loudest voices supporting the idea that 3IATLAS might be something other than a natural object. Loeb, known for his controversial theory about the interstellar object WAM or more being a potential probe, suggested that 3IATLAS could similarly be an artifact, perhaps part of a larger interstellar network, a probe deliberately sent by an alien civilization to explore or monitor the space around our solar system. Loeb argued that the unusual trajectory and the strange properties of the object could be consistent with the idea of it being an artificial probe, perhaps even intentionally hidden from view in some way. Loeb's theories drew sharp criticism from many in the scientific community, who dismissed the idea of 3IATLAS as an alien probe as speculative and lacking in evidence. But Loeb and his supporters continued to press the argument, pointing to the object's highly unusual behavior as evidence that it couldn't be explained by natural processes alone. The lack of water ice, the faint tail, and the highly specific trajectory all seemed to Loeb to be signs of something far more sophisticated than a simple comet. He even pointed out that the apparent lack of a clear rotation, the absence of periodic changes in brightness that one would expect from a spinning body, could be another indicator that 3IATLAS wasn't a natural object at all, but rather a carefully constructed device. While the idea that 3IATLAS might be a probe from an alien civilization remained highly controversial, it was impossible to ignore the way the object's strange characteristics defied conventional explanations. The very fact that the object had traveled across vast stretches of interstellar space, arriving in our solar system with so many anomalies, begged the question of whether we were dealing with something beyond our understanding of natural celestial bodies. The possibility that 3IATLAS might be a product of extraterrestrial intelligence forced astronomers to question their assumptions about the universe and the kinds of phenomena that could exist beyond our current knowledge. Meanwhile, the idea that 3IATLAS might be an artificial probe wasn't the only controversial theory circulating within the scientific community. Some researchers also suggested that the object could be a fragment of a larger body that had been broken apart by a catastrophic event. This idea proposed that 3IATLAS could have originally been part of a much larger interstellar object, one that had been torn apart by tidal forces or a collision with another body. Over time, smaller fragments from this shattered object might have been scattered across the galaxy, with 3IATLAS being one of the pieces that had survived the journey. This theory was intriguing, as it could explain the object's strange chemical composition, its faint tail, and its seemingly erratic motion. But like the idea of an alien probe, it was speculative and unproven. In the midst of these wild theories, there was also the more conventional view that 3IATLAS was simply an exceptionally strange comet from another star system, with a composition and behavior that defied the usual rules. This theory, while more in line with traditional cometary science, still couldn't fully explain the object's unusual features. Its trajectory, its lack of detectable water, its faint tail, all of these factors continued to challenge the conventional models. Still, this theory remained the most widely accepted among many astronomers, who felt that 3IATLAS was an outlier, a cosmic oddity that pushed the boundaries of what was known about comets and interstellar objects. The theories and speculations about 3IATLAS reflected the growing recognition that we were dealing with something unprecedented. Whether it was a comet from a distant star system, a fragment of a shattered interstellar object, or even an artificial probe sent by an alien civilization, 3IATLAS had revealed that the universe still had many surprises in store. And as the object continued its journey through our solar system, one thing was clear: it had forever changed the way we think about the cosmos, forcing us to confront the limits of our knowledge and imagination. As the astronomical community continued to struggle with the mystery surrounding 3IATLAS, one thing became undeniably clear: this object was more than just a passing anomaly. The questions raised by its strange composition, trajectory, and behavior were pushing the boundaries of our scientific knowledge in ways that could have far-reaching implications. With every new observation and every attempt to model its movements and chemistry, scientists were forced to reconsider old assumptions about the nature of comets, interstellar bodies, and even the fundamental forces that govern the universe. The very presence of 3IATLAS in our solar system had opened up an entirely new field of study. In the past, astronomers had largely focused their attention on objects that were either native to our solar system, like comets and asteroids, or those that passed through briefly, like meteors. But 3IATLAS was different. It was a visitor from beyond the bounds of our sun's gravitational influence, an interstellar object, something that had traveled across the vast reaches of space, possibly for millions or even billions of years. It was not just another space rock passing through our cosmic neighborhood. It was a representative of an entirely different class of objects that we had barely begun to understand. The discovery of 3IATLAS was part of a broader trend in astronomy, one that had begun with the detection of the first interstellar object, Oumuamua, in 2017, and continued with the identification of These objects, which originated from other star systems, were radically different from the bodies that populate our own solar system. They were not bound by the sun's gravity, and unlike comets from our own system, had no predictable cycles or orbit. The appearance of 3I-ATLAS, a comet with a bizarre chemical composition, a strange trajectory and an unpredictable gas cloud, confirmed what many had suspected. Our solar system, it seemed, was only one tiny corner of a much larger and more complex universe, and that universe was filled with objects that defied every assumption we had made about the behavior of comets, asteroids and other celestial bodies. In a very real sense, 3I-ATLAS was a cosmic ambassador, a messenger from the far reaches of interstellar space. Its passage through our solar system was a rare and extraordinary event, an event that forced scientists to confront the vastness of the universe and the realization that our understanding of it was still in its infancy. For decades, astronomers had assumed that most objects in space followed predictable patterns, obeying the same laws of physics that governed the motion of planets and moons. But 3I-ATLAS had shown that the universe was far more mysterious and unpredictable than we had imagined. The object's behavior suggested that there were forces at play that we had yet to fully understand, and that there were aspects of space and time that were still hidden from view. In the aftermath of 3I-ATLAS's discovery, the astronomical community began to shift its focus. The object's strange behavior had revealed a gap in our knowledge of interstellar objects. For years, scientists had been focused on studying objects within our solar system, where they had the luxury of observation over extended periods of time. But 3I-ATLAS, with its rapid trajectory and fleeting presence, highlighted the challenges of studying objects that passed through only briefly, before disappearing into the depths of space. It became clear that there was a need for new technologies, new telescopes, and more sophisticated methods of tracking and analyzing these interstellar visitors. One of the major implications of 3I-ATLAS's appearance was that it encouraged astronomers to look beyond the boundaries of our solar system. For the first time, astronomers began to realize that there might be entire populations of objects out there, drifting through the galaxy just waiting to be discovered. Interstellar objects like 3I-ATLAS were not just rare accidents, but part of a much larger population of cosmic wanderers. These objects could contain valuable information about the early stages of star system formation, and their study could reveal key insights into the conditions that exist in other parts of the galaxy. As scientists began to track the paths of other interstellar objects, it became clear that we were only scratching the surface of a new and exciting frontier in astronomy. At the same time, 3I-ATLAS's behavior had profound implications for our understanding of comets and their evolution. The discovery that the object's gas cloud was primarily composed of carbon dioxide, an element far less common in our own solar system's comets, suggested that comets could evolve in dramatically different ways, depending on the conditions of their home star systems. Comets were no longer seen as simple frozen relics of the early solar system, but as complex and diverse bodies that could be shaped by their environments in ways we had never imagined. The study of 3I-ATLAS had the potential to reveal the rich diversity of cometary activity, offering new insights into the ways that comets form, interact with their environments, and evolve over time. This shift in understanding also had broader implications for the study of planetary formation. By studying the composition and behavior of interstellar objects like 3I-ATLAS, scientists could begin to explore how planetary systems in other parts of the galaxy might differ from our own. The chemical makeup of 3I-ATLAS, with its carbon dioxide-rich composition and unusual gas emissions, suggested that planets in other star systems could be vastly different from the ones we are familiar with. If interstellar objects like 3I-ATLAS were representative of a broader class of bodies, then the process of planetary formation in other systems could be dramatically different, influenced by factors such as the age of the star, the chemical composition of the surrounding nebula, and the distance from the star itself. In some ways, the study of 3I-ATLAS was like opening a window into a completely different universe, one where the rules of planetary formation, cometary behavior, and even the fundamental forces of physics could operate in ways we had never before imagined. Each new discovery about 3I-ATLAS seemed to add a new layer of complexity to our understanding of the universe. The more we learned, the more questions arose, and the more it became clear that the mysteries of space were far deeper than we had ever suspected. But perhaps the most profound impact of 3I-ATLAS's visit was its role in sparking new interest in the search for extraterrestrial life. While the scientific community had long debated the existence of life beyond Earth, The discovery of interstellar objects like 3I-ATLAS had a transformative effect on the way we thought about the possibility of life in the galaxy. The fact that an object from another star system could pass through our solar system was a stark reminder that the universe was vast and full of surprises. If objects like 3I-ATLAS could travel across such vast distances, then it seemed plausible that life too might exist on planets orbiting distant stars, waiting to be discovered. The implications of this were far-reaching. 3I-ATLAS was a reminder that we are not alone in the universe, and that there is much more out there to discover. The study of interstellar objects, and the search for other planets that might harbor life, would become an increasingly important focus of space exploration. Just as we had begun to peer deeper into the farthest reaches of our own solar system, we now had the tools to look beyond, to consider the vastness of the galaxy and the possibility that life could exist in places we had never imagined. As 3I-ATLAS continued its journey through our solar system, its passage was a moment of profound reflection for astronomers and the public alike. In many ways, it was a reminder of how much we still don't know about the universe, and how much there is left to explore. Its strange characteristics and inexplicable behavior forced us to rethink our assumptions, to challenge our understanding of the laws that govern the cosmos, and to recognize that we are only just beginning to scratch the surface of the vast mysteries that lie beyond our own star system. The legacy of 3I-ATLAS would undoubtedly have a lasting impact on the field of astronomy, inspiring new research, new technologies, and new questions about the nature of space itself. It had shown us that even the most familiar objects, comets, asteroids, and interstellar visitors, could hold secrets beyond our wildest imagination, and in doing so it had opened a door to a future of discovery and exploration that promised to be just as mysterious and awe-inspiring as the object that had started it all. As 3I-ATLAS made its fleeting passage through our solar system, astronomers were left grappling with a deeper question: how do we study objects like this? Objects that appear seemingly out of nowhere, with mysterious origins and unpredictable behavior. While the object's brief visit had illuminated the vast mysteries of the cosmos, it had also revealed just how ill-prepared our current scientific infrastructure was to fully unlock the secrets of interstellar visitors. The discoveries made during 3I-ATLAS's brief passage through the solar system had opened up a world of possibilities, but they also highlighted the urgent need for new technologies, better tools, and more sophisticated methods of observation if we were to fully understand these cosmic wanderers and their impact on our understanding of the universe. One of the most significant challenges in studying 3I-ATLAS was its speed and the short time window in which scientists had to observe it. At over 130,000 miles per hour, 209,000 kilometers per hour, the object was traveling so fast that it barely slowed down as it passed through the solar system. For comparison, this is around 70 times the speed of a bullet. Its speed made it difficult to track for extended periods, and by the time the astronomical community had fully mobilized to study the object, it was already on its way out of the solar system. The high velocity of 3I-ATLAS meant that the window for observation was incredibly narrow, just a few months in some cases, to capture data before the object vanished into the deep space beyond the reach of our instruments. This fast-paced, limited time frame represented a critical challenge for astronomers, who were accustomed to studying objects that spent years or even decades within our observational reach. But the need to study interstellar objects is not confined to just one rare visitor. The increasing discovery of other interstellar bodies like 2I Borisov and, most recently, 3I-ATLAS underscores the growing importance of having more capable tools and a deeper understanding of these fleeting objects. If we hope to uncover the full mysteries of the universe, it's clear that the tools we currently have in place, powerful though they are not enough. New, more sophisticated space telescopes, better tracking systems, and a greater emphasis on real-time data collection will be essential for future missions that hope to study these objects in greater detail. One of the first steps toward addressing these challenges is to develop telescopes that can track objects at high speeds with much greater precision. Most telescopes currently in use are excellent at observing objects that are stationary or moving slowly. However, objects like 3I-ATLAS, traveling at extreme velocities, require telescopes that can react quickly and track them in real time. New space-based telescopes, like the upcoming James Webb Space Telescope, JWST, are designed to provide more accurate data on distant objects. But tracking an interstellar object like 3I-ATLAS requires an ability to monitor high-speed trajectories with far greater precision than ever before. The JWST, with its advanced infrared capabilities, will likely provide key insights into the composition of future interstellar objects, but its ability to track their movement in real time, as 3IATLAS showed, is still limited by its design. What we need are dynamic, flexible tracking systems that can capture real-time data about fast-moving interstellar objects. To address this, one possible solution lies in an expanding network of telescopes stationed around the world, in space, and even on other planets. Combining the efforts of observatories on Earth, such as the recently upgraded Very Large Telescope VLT in Chile, with advanced instruments in orbit, could allow scientists to track these objects continuously, even as they pass by our solar system at high speed. In the case of 3IATLAS, having a coordinated global network of observatories equipped with the latest tracking software would have allowed for a more comprehensive and continuous study of the object, without relying on the limitations of any single telescope or location. But it's not just about improving telescopes. It's also about developing new technology that can capture data on these objects that's never been done before. One of the biggest challenges with objects like 3IATLAS is the sheer volume of data that needs to be processed in real time. When studying a rapidly moving object, data stream is vast and comes in a variety of forms, from optical images to infrared and radio signals. Traditional methods of analyzing this data are often too slow to keep up with the speed of the object's movement. As a result, more advanced data processing systems, perhaps powered by artificial intelligence or machine learning, would be required to handle the enormous amounts of data that come in during the brief observation windows of fast-moving interstellar objects. These systems would need to be capable of identifying critical data points from a much larger data set, flagging key moments in the object's trajectory and ensuring that scientists don't miss any important details that could shed light on its origins and composition. In addition to improving telescopes and data processing systems, there is also the issue of data sharing. Currently, data about objects like 3IATLAS is collected by a variety of organizations, including space agencies like NASA, the European Space Agency, ESA, and private observatories around the world. However, these organizations do not always share data in real time. For instance, it wasn't until the object was well on its way out of the solar system that full, detailed observations were publicly shared. A more coordinated, open data approach could allow astronomers around the world to work together more effectively in real time, sharing their observations and theories, and piecing together the puzzle of interstellar objects like 3IATLAS more quickly and more comprehensively. This collaborative approach would not only accelerate our understanding of these objects, but could also provide valuable insights into the broader field of space exploration. As technology improves, it will also become increasingly possible to study interstellar objects through direct observation by spacecraft. While the idea of sending a probe to study an object like 3IATLAS seems far-fetched, the possibility of such missions is becoming more realistic. For example, NASA's recent successful deployment of the Perseverance rover to Mars, as well as the ongoing planning for future missions to the outer planets, show that interplanetary travel is becoming more feasible. In the long term, missions to intercept or rendezvous with interstellar objects may be the key to uncovering their true nature. A dedicated spacecraft could fly out to an interstellar object passing by or even landing on it, to gather data in ways that are simply not possible with telescopes. A mission like this would be expensive, and it would require long-term planning and technological innovation, but the scientific potential is enormous. In fact, the idea of sending a spacecraft to visit a comet or interstellar object is already on the horizon. NASA's Comet Interceptor mission, scheduled for launch in 2029, aims to study a pristine comet that has never passed through the inner solar system, and the European Space Agency, ESA, is working on similar missions. These missions, while still focused on comets from our own solar system, could serve as a stepping stone for future missions to interstellar visitors like 3IATLAS. The technologies developed for these missions, such as advanced propulsion systems, real-time communication with spacecraft, and enhanced sensors capable of analyzing distant objects, could be repurposed for future interstellar missions. Moreover, these missions could also help to develop the kind of long-duration space travel needed to send probes to distant parts of the galaxy. While 3IATLAS was a fleeting visitor, the next interstellar object may not be so far away, and with advancements in spacecraft design, we could find ourselves studying these objects up close and personal in the near future. This would mark a major leap forward in space exploration, enabling us to explore interstellar space not just from afar but with first-hand knowledge of the objects that reside within it. As the study of 3IATLAS continues, And as we look forward to the discovery of other interstellar visitors, it is clear that our current methods of observation are only the beginning. The future of space exploration is one where we will rely on advanced telescopes, innovative data processing systems, and perhaps even spacecraft missions to uncover the true nature of these objects. The discovery of interstellar visitors like 3IATLAS has opened the door to a new era of exploration, one where we can push the limits of our technology and our imagination and seek to understand the mysteries of the universe in ways we never thought possible. The brief but profound encounter with 3IATLAS left us with more than just scientific questions. Its passage through the solar system illuminated not only the mysteries of space but also our place within it, forcing us to confront the vast unknowns of the universe. Objects like 3IATLAS challenge the very foundations of our understanding, revealing the infinite scale of the cosmos and our small, fleeting existence within it. But just as importantly, it reminds us that there is still so much we don't know, and that the universe is filled with surprises that continue to defy even our most advanced knowledge. For astronomers, the encounter with 3IATLAS has led to a significant shift in the way we think about interstellar objects. For centuries, our understanding of the universe was confined largely to our solar system: planets, moons, asteroids, comets. These were the objects that filled our study of the cosmos, and for much of human history we assumed that these were the only types of celestial bodies we would ever encounter. But the discovery of interstellar objects, beginning with 1I Oumuamua in 2017, and followed by 2I Borisov in 2019 and 3IATLAS, has forever changed that assumption. These objects, with their mysterious origins and unpredictable behaviors, are forcing scientists to expand their definitions of what constitutes a comet or asteroid. They are unlike anything we've encountered before and challenge the very frameworks of astronomy that we've relied on for centuries. The fact that we are now able to study interstellar objects as they pass through our solar system has opened up an entirely new field of astronomical research. This area, which is still in its infancy, holds immense potential for discovering objects and phenomena we never even imagined existed. 3IATLAS, with its baffling properties, has set a new benchmark for what astronomers can expect to see in the future. The encounter with this object could be the first of many, and as technology continues to advance, we will be able to study these cosmic wanderers in greater detail than ever before. The study of interstellar objects like 3IATLAS could unlock secrets about the formation of planets, stars and galaxies that we had only hypothesized about until now. But beyond the scientific advancements, the arrival of 3IATLAS also raises broader existential questions about life and the universe. For centuries, humanity has looked up at the night sky, wondering if we are truly alone in the cosmos. The discovery of interstellar objects, especially those with unusual characteristics, brings us face to face with the idea that life beyond Earth may not only be possible, but could be more common than we've thought. While 3IATLAS itself is unlikely to contain life, its passage reminds us that the universe is filled with countless other objects, some of which may have traveled through star systems that harbored life, or could even still harbor it today. In the wake of 3IATLAS's visit, questions about extraterrestrial life have once again come to the forefront of scientific discourse. If interstellar objects can travel across the vast distances between stars, could some of them be carrying evidence of life or perhaps even life itself? Could there be other messengers like 3IATLAS, sent from distant star systems, carrying clues to the conditions that foster life? And if interstellar objects are indeed common, could we one day encounter a probe, a relic, or even a signal from a civilization far older than ours? These questions, once the domain of science fiction, are now part of the conversation among serious scientists. The notion that life could be more widespread in the universe than we previously thought is an exciting and humbling one. If 3IATLAS and similar objects have traveled across vast stretches of interstellar space, it suggests that the universe is not a vast empty void, but a dynamic and interconnected web of objects and forces, each with its own history and potential for life. It also forces us to consider our own place in the cosmos. What if we too are just one of many civilizations scattered across the galaxy, temporary blips in the vast timeline of the universe? The discovery of 3IATLAS and other interstellar objects challenges us to think about the longevity of civilizations, the possibility of their collapse, and the interconnectedness of all things in the universe. Moreover, the fact that 3IATLAS is an object that traveled from another star system emphasizes how fragile and interconnected the fabric of the universe is. The universe is not just a collection of isolated, static objects. It is an active, evolving system in which even the smallest objects can have far-reaching impacts. Objects like 3IATLAS have been drifting through space for millions or even billions of years, traveling across the galaxy in search of their next encounter. They serve as a reminder of the vastness of the cosmos and of the cosmic forces that shape the destiny of all objects, whether they are small comets or massive stars. The arrival of 3IATLAS forces us to reckon with the idea that there are forces in the universe beyond our control, forces that shape the lives of stars and planets, and that our existence is but a fleeting moment in the grand scheme of things. On a more practical level, the discovery of interstellar objects like 3IATLAS presents a unique opportunity for scientific advancement in space exploration. The study of these objects not only gives us a chance to learn more about the early stages of stellar and planetary formation, but it also opens the door to a new frontier in space exploration. While the idea of sending a spacecraft to study an object like 3IATLAS may seem like science fiction, the technological advancements made in recent years, such as NASA's successful Perseverance rover mission to Mars and the upcoming James Webb Space Telescope, make such missions increasingly plausible. Over the next few decades, the possibility of sending spacecraft to meet and study interstellar objects in person may no longer be a distant dream. As we develop better propulsion technologies and more advanced space exploration methods, the idea of intercepting a visitor from another star system may become a reality. In fact, the potential for such missions may be closer than we think. Space agencies like NASA and the European Space Agency, ESA, have already begun planning missions that could study distant comets or asteroids in far greater detail than was previously possible. These missions could serve as a foundation for future expeditions to interstellar objects, and as the capabilities of space telescopes and tracking systems continue to improve, we will be able to detect these objects earlier in their journeys, giving us more time to study them and even plan missions to intercept them. A study of interstellar objects like 3IATLAS could thus be the gateway to a new age of space exploration, one that stretches beyond the confines of our own solar system. However, studying 3IATLAS and other interstellar visitors is not just about learning more about the universe. It is also about understanding our place within it. The arrival of these cosmic wanderers forces us to reflect on the fragility of life and the universe, and to consider the potential for life elsewhere. As we continue to explore the cosmos, the question of whether we are alone in the universe becomes more urgent. Every new discovery, whether it's an interstellar object like 3IATLAS, a distant exoplanet, or a mysterious cosmic phenomenon, reminds us that the universe is vast, unknown, and full of potential. Whether or not we are the only intelligent species in the galaxy is a question that will likely remain unanswered for some time, but the search for that answer is one of the most profound quests of our time. As we look to the future, the study of objects like 3IATLAS will be an integral part of our journey of discovery. These objects are not just scientific curiosities, they are messengers from the farthest reaches of the galaxy, offering us clues about the origins of life, the formation of planets, and the forces that shape the universe. They are a reminder that the universe is full of mysteries that we have yet to unravel, and that our place in the cosmos is still waiting to be understood. The study of 3IATLAS and its interstellar counterparts will continue to inspire generations of scientists and explorers, and may one day lead us to discoveries that change our understanding of life, the universe, and everything in it. As the astronomical community continues to dissect the mysteries of 3IATLAS, one undeniable fact emerges: the implications of its passage through the solar system extend far beyond the scientific data it provided. The encounter with this interstellar wanderer serves as a landmark moment in the ongoing evolution of space exploration. It reminds us that we are living in an era of rapid advancements in technology, discovery, and knowledge that will shape the future of how we explore space, and how we approach the biggest questions about life, the universe, and our place within it. While 3IATLAS may have been a singular fleeting visitor, it marks the beginning of a larger, ongoing exploration that will stretch into the vastness of the cosmos. The arrival of interstellar objects like 3IATLAS is not a mere curiosity. Rather, it represents the start of a new phase in humanity's exploration of the universe. For centuries, we have looked up at the night sky with awe and wonder, gazing at distant stars and contemplating the possibility of life beyond Earth. But as our technology has advanced, so too has our ability to reach further into the cosmos. With each new discovery, we find ourselves questioning our assumptions, challenging our previous boundaries, and realizing that the universe is far more complex and vast than we had ever imagined. One of the most significant consequences of 3IATLAS's visit is the heightened interest in and investment in interstellar exploration. Until recently, our focus in space exploration has been mostly within our solar system, exploring planets like Mars, Venus, and Jupiter, studying asteroids and comets, and learning more about the inner workings of our own cosmic neighborhood. While these missions have been immensely valuable, 3IATLAS has shown us that the universe beyond our solar system is just as accessible, if not more so, than the space we can observe with traditional methods. As the first interstellar object discovered, Oumuamua, captured the world's attention in 2017, scientists and space agencies around the globe began to see the potential of exploring objects from beyond our solar system. 3IATLAS has only deepened this sense of possibility. Given its high speed and the challenges of tracking objects moving through space at such rapid velocities, we are left with a pressing question: how can we improve our methods of tracking, observing, and even reaching interstellar objects? The technologies required for this kind of space exploration are vastly different from those used for studying planets or moons within our solar system. The sheer distance and speed of interstellar objects like 3IATLAS demand new strategies for early detection, data collection, and even mission planning. In the near term, the creation of dedicated space telescopes that can detect objects traveling at high speeds much earlier in their journey will be crucial. The earlier we can detect these objects, the more time we have to study them in detail. This can help mitigate the challenges presented by their fast trajectories, which often leave us with limited windows of observation. By developing specialized telescopes that can detect these objects long before they arrive in our solar system, astronomers will have the opportunity to plan and coordinate more comprehensive observations, increasing the likelihood of gathering valuable data. These telescopes will also need to be able to track high-velocity objects in real time, ensuring that we don't miss crucial moments in their path. Furthermore, building advanced space probes to study interstellar objects at close range will become an increasingly important goal for future space exploration. While sending a probe to intercept an object like 3IATLAS seems like a daunting challenge, it is not an impossible one. Spacecraft like the New Horizons probe, which made history by visiting Pluto in 2015, have already demonstrated the feasibility of long-term, long-distance missions that can travel vast distances over the course of years or decades. Missions to interstellar objects, whether they involve flybys or even landing on these objects, may be a natural extension of this technological progress. These missions would provide invaluable data on the composition, structure, and history of interstellar bodies, helping us piece together the story of our galaxy and beyond. The idea of reaching interstellar objects is exciting not only for scientific discovery but also because it brings us closer to an era of human exploration beyond the solar system. Today, space exploration is largely focused on robotic missions, and while these have been extraordinarily successful in uncovering secrets about our solar system, the true challenge lies in sending humans beyond the confines of Earth's atmosphere and orbit. Though sending humans to an interstellar object like 3IATLAS may still be far beyond our current capabilities, the technological advancements required to study these objects will play a crucial role in the development of technologies that could one day make human missions to other stars possible. Human space exploration beyond our solar system is still in the realm of science fiction, but the fact that we are already contemplating missions to interstellar objects represents a major step toward making that future a reality. With advanced propulsion technologies like nuclear thermal propulsion or even more speculative technologies like fusion or antimatter propulsion, humanity could one day embark on voyages that take us to distant stars. While that day may be far off, the groundwork for such missions will be laid through our growing ability to study interstellar objects and navigate the vast distances between the stars. As 3IATLAS has shown us, the universe is not as distant as it once seemed. Moreover, the scientific potential of studying interstellar objects extends far beyond just understanding their composition. As we learn more about the conditions in other star systems, we begin to open new avenues of research into the formation of planets and stars, as well as the possibility of extraterrestrial life. The fact that objects like 3IATLAS can travel across the galaxy for billions of years, carrying with them the chemical remnants of their star systems, opens up entirely new ways of looking at the evolution of the universe. These objects are time capsules that hold within them clues to the very origins of stars and planets, and perhaps even the ingredients for life itself. In the context of the search for extraterrestrial life, interstellar objects like 3IATLAS offer a tantalizing possibility. What if these objects have brought with them traces of life from distant star systems? While we are still a long way from proving the existence of extraterrestrial life, The study of interstellar objects could give us new tools to answer that question. If life exists elsewhere in the universe, these objects may carry evidence of it, whether in the form of organic molecules, microbial life, or even ancient signatures of past civilization. As we continue to study these visitors, we may one day find the evidence that we are not alone, and that life has flourished elsewhere in the galaxy, just as it has on Earth. Beyond the pursuit of scientific knowledge, the study of interstellar objects has a deeper philosophical impact. 3IATLAS and its fellow travelers are stark reminders of the transient nature of all things in the cosmos. They remind us that everything we know, including our solar system and even our planet, is part of a much larger, ever-changing universe. Objects like 3IATLAS, which travel across galaxies and can spend millions or billions of years moving through the void, are symbols of the vastness and impermanence of the universe. The brief time they spend within our reach is but a moment in the eternal timeline of the cosmos, a fleeting encounter that reminds us of how small and fragile our existence is in the grand scheme of things. Yet even in their brief passage, these objects offer us the chance to expand our knowledge and to reflect on the nature of existence itself. In the end, 3IATLAS is more than just an object of scientific study. It is a catalyst for new ways of thinking about the universe, space exploration, and our place in the cosmos. As we continue to study this interstellar traveler, and as we develop the tools to study many more in the future, we will not only deepen our understanding of the universe but also explore the deep existential questions that lie at the heart of human curiosity. The search for answers about life, about the origins of the universe, and about our role in the cosmic story will continue to drive humanity's exploration of the stars. And 3IATLAS in all its mystery will be remembered as the object that helped push us further into the unknown, forever changing the way we think about our place in the vast, awe-inspiring universe. The passage of 3IATLAS through our solar system, while brief, has left a lasting mark on both the scientific community and the general public. The object's enigmatic nature, its chemical composition, and its baffling trajectory have raised questions that will take years, if not decades, to fully answer. However, one thing is certain: its visit is just the beginning of a new era in space exploration. The implications of this first confirmed interstellar visitor are profound, not only in terms of the immediate scientific insights, but also in the long-term future of human exploration beyond the confines of our solar system. As we look forward, the study of interstellar objects will undoubtedly become a priority for space agencies and researchers across the globe. The discovery of 3IATLAS has shown us that the universe is far more connected and dynamic than we once believed. Interstellar objects are not isolated or rare anomalies. They are messengers from the vast expanses of space, carrying with them information about star systems, planetary formation, and perhaps even the conditions necessary for life. The study of these objects offers an unprecedented opportunity to learn about other solar systems and the broader processes that govern the cosmos. The fact that 3IATLAS was able to traverse the galaxy for millions or even billions of years, undetected, only to be discovered during its fleeting passage through our solar system, reinforces the idea that the universe is full of hidden wonders waiting to be uncovered. However, studying these interstellar objects presents significant challenges. As we've seen with 3IATLAS, the short duration of their visibility, combined with their high velocities, makes it difficult to track them long enough to study them in detail. Most objects in our solar system, from planets to comets and asteroids, follow stable, predictable orbits, but interstellar objects like 3IATLAS have no such predictable paths. They are on trajectories that take them through the solar system only once, and with limited observation windows. In the case of 3IATLAS, by the time astronomers had fully grasped its significance, the object was already speeding away from the Sun, making further study more difficult. This is where the next generation of space telescopes and observatories comes into play. The lessons learned from 3IATLAS's visit will likely lead to more advanced instruments capable of detecting and tracking interstellar objects earlier in their approach. Telescopes that specialize in observing high-velocity objects, perhaps ones specifically designed to study objects on hyperbolic orbits, will be key in making future interstellar object discoveries possible. The advent of advanced space telescopes, such as the James Webb Space Telescope (JWST), promises to revolutionize our ability to study distant objects, not just within our solar system, but from beyond. JWST's infrared capabilities will allow astronomers to detect objects that are too faint or distant for current optical telescopes to observe. For objects like 3IATLAS, this could mean the difference between seeing them as they pass through the solar system and missing them entirely. Furthermore, next-generation telescopes, combined with AI and machine learning technologies for real-time data processing, could make it possible to track fast-moving interstellar objects with unprecedented precision. This would not only help us gather more detailed information on these objects, but also allow us to better plan for potential future encounters, giving us the tools needed to study them during their fleeting visits. However, the technological advances required to track and study these objects go beyond telescopes and observation techniques. In the future, we may need to send spacecraft to physically visit these interstellar wanderers. As of now, the idea of sending a spacecraft to an object like 3IATLAS seems far-fetched. After all, the object was traveling at speeds that would make it difficult to intercept with current propulsion technology. Yet space agencies are constantly working on advancements in propulsion systems, and the technology to send spacecraft farther and faster is improving. Proposals for advanced propulsion systems such as nuclear thermal propulsion, ion drives, or even fusion-based systems are being actively studied. These technologies, while still in the experimental or conceptual stages, could eventually make it possible to send missions that could intercept interstellar objects in the future. The ability to send a spacecraft to study an interstellar object up close would be a groundbreaking achievement, providing insights into their structure, composition, and even their history. It would also give us a chance to gather the kinds of data that telescopes cannot provide: the texture of the object's surface, the nature of its gases, and even the possibility of detecting organic molecules that could have been carried across space. One of the most exciting aspects of this kind of exploration is that it could provide us with answers to some of the most profound questions about the universe. Questions about the origins of life and whether life might exist elsewhere. As we study interstellar objects like 3IATLAS, we gain new insights into the chemical makeup of distant star systems. Could some of the building blocks of life have traveled from other solar systems, carried on the backs of objects like 3IATLAS? While 3IATLAS itself is unlikely to contain life, the study of these objects could provide clues about the chemical processes that lead to the formation of life. If interstellar objects are composed of the same organic molecules found on Earth, it could suggest that the conditions necessary for life are more common in the galaxy than we had previously thought. This idea that life could have originated elsewhere in the universe, and that the seeds of life may have spread from one star system to another, is not new. The theory of panspermia, which suggests that life could be carried between planets and star systems on comets, asteroids, or even interstellar dust, has been around for centuries. The discovery of 3IATLAS, with its strange chemical composition and the possibility that it came from a distant star system, offers a tantalizing piece of evidence that supports this theory. While it's still far too early to say definitively whether 3IATLAS or any other interstellar object contains life, its passage forces us to reconsider the conditions under which life might arise, spread, and endure across the galaxy. Beyond the search for life, the study of interstellar objects like 3IATLAS also has profound implications for our understanding of the formation and evolution of planets and stars. These objects are essentially time capsules, carrying with them the chemical fingerprints of the star systems they came from. By studying these objects, astronomers can learn more about the processes that govern the formation of stars and planets, including the role that chemical elements play in shaping the environments that could support life. 3IATLAS's carbon dioxide-dominated composition, for instance, could provide clues about the early stages of its parent star system, giving us a glimpse into the conditions that led to its formation and the factors that influenced its evolution. As we continue to develop our understanding of interstellar objects, it will become increasingly clear that they are not just distant curiosities, but key players in the ongoing story of the universe's creation. These objects, which travel across vast stretches of space, are the remnants of ancient star systems, and their study could unlock secrets about the early history of the galaxy. By learning from them, we will deepen our understanding of how stars and planets form, how life might emerge, and how the universe itself has evolved over billions of years. However, the most profound impact of 3IATLAS's visit may be the way it forces us to think about our place in the universe. As we continue to study these interstellar travelers, we begin to realize just how small we are in the vast expanse of space. Our solar system is just one of billions of star systems scattered across the galaxy, and each of those systems contains untold numbers of objects that are just as fascinating and mysterious as 3IATLAS. The more we discover about the universe, the more we realize that we are a tiny part of something much larger, a vast interconnected web of stars, planets, and celestial bodies that stretches across space and time. This realization, however humbling, is also profoundly inspiring. It reminds us that humanity is on the precipice of something greater than we can imagine, a future in which space exploration is no longer confined to our own solar system, but extends far beyond, into the vast unknown of interstellar space. While the journey to send humans beyond our solar system may still be far off, the study of objects like 3IATLAS is laying the groundwork for that future. It's teaching us how to think bigger, how to ask deeper questions, and how to approach the universe with the curiosity and determination that has defined us as a species. As we move forward, we can look to 3IATLAS as a symbol of what lies ahead, an invitation to explore the stars and uncover the mysteries of the cosmos, one interstellar object at a time. The passage of 3IATLAS through our solar system, though brief, has left us with far more than just a collection of scientific data. It has sparked a deep and profound contemplation about humanity's place in the universe. As we stand at the cusp of new frontiers in space exploration, the mysteries surrounding 3IATLAS force us to confront questions that go beyond the realm of science. Questions about our existence, the nature of life, and our connection to the universe. This is the cosmic moment that calls not just for analysis of data, but for introspection about who we are and how we fit into the vast, incomprehensible expanse of space. In some ways, the discovery of 3IATLAS mirrors humanity's ancient curiosity about the stars, a curiosity that has fueled our dreams and aspirations for millennia. From the earliest civilizations, humans have looked up at the night sky, awed by its vastness and mystery. In ancient times, the stars were seen as the domain of gods and supernatural forces. They held secrets and promises that were beyond human comprehension. Over time, as our understanding of the cosmos expanded, those same stars became objects of scientific inquiry. Yet no matter how much we learn, the universe remains an enigmatic and humbling force, a reminder that there is much more beyond our reach. 3IATLAS, as the first confirmed interstellar visitor to pass through our solar system, has reignited that ancient sense of wonder. Its very existence challenges our assumptions about the solar system, the galaxy, and the broader universe. For centuries, we thought of our solar system as a self-contained entity, bound by the gravitational pull of our sun. The idea of an object from another star system, traveling across vast distances of interstellar space, has forced us to reconsider not just our solar system, but our place within the galaxy itself. The sheer scale of 3IATLAS's journey, traveling for millions or billions of years through the vast emptiness between stars, is a powerful reminder of how small and fleeting our own existence is in the context of the universe's history. As we grapple with these new understandings, the presence of 3IATLAS forces us to confront existential questions that we have been asking for millennia. What does it mean to be human in a universe that is so vast and seemingly indifferent to our existence? Are we alone in the cosmos, or are we just one of many intelligent species scattered across the galaxy, each with its own fleeting moment in time? The encounter with 3IATLAS, like the discovery of exoplanets and the search for extraterrestrial life, is part of a much larger philosophical and existential conversation about life's origins, the nature of intelligence, and the future of our species. For some, the arrival of an interstellar object like 3IATLAS stirs a sense of isolation, the vast distances between stars, and the realization that objects like 3IATLAS have been drifting across the galaxy for billions of years without interacting with anything, can feel daunting. The universe seems vast, indifferent, and impersonal. It's easy to feel small, insignificant, and alone in the face of such overwhelming scale. Yet, for others, the passage of 3IATLAS represents a reminder of our potential for discovery, for exploration, and for connection. The fact that we are even able to observe and study such an object, one that has traveled across unimaginable distances, speaks to the extraordinary capabilities of human curiosity, innovation, and determination. This duality between existential isolation and the awe of discovery captures the essence of what it means to be human in the modern age. As we push the boundaries of space exploration, we find ourselves both humbled by the vastness of the universe and exhilarated by our capacity to understand it. The mysteries of the cosmos, once seen as unknowable, are slowly becoming more accessible. The study of interstellar objects like 3IATLAS is just the beginning. Every new discovery about the universe invites us to ask deeper questions. How did we get here? What lies beyond the stars? And what is our place in the larger tapestry of existence? One of the most profound implications of studying interstellar objects like 3IATLAS is the realization that we are not alone in the universe in the way we once thought. 3IATLAS itself may not contain the answer to the question of extraterrestrial life, but its existence invites us to consider that there may be more out there than we can imagine. The very fact that we are able to observe an object from another star system suggests that the universe is filled with hidden wonders, many of which we have yet to discover. And if objects like 3IATLAS are out there traveling across galaxies and star systems, then perhaps there are other forms of life, or remnants of past civilizations, waiting to be found. The search for extraterrestrial life has long been one of humanity's greatest quests, and the discovery of interstellar objects only deepens that search. Could 3IATLAS or some other interstellar object be carrying clues about the conditions that foster life? Could it be that life itself has traveled across space, carried on the backs of objects like 3IATLAS, in a cosmic version of panspermia, the idea that life spreads between planets and star systems, carried by comets, asteroids, or interstellar dust? While we are still a long way from answering these questions, the mere possibility is enough to inspire a sense of wonder and possibility that transcends the boundaries of science. If life can travel across the galaxy, then perhaps the universe is teeming with the potential for life, waiting to be discovered. The study of interstellar objects like 3IATLAS is the first step in this search, opening up new frontiers for humanity's exploration of the cosmos. However, the existential implications of studying objects like 3IATLAS go beyond just the search for life. They force us to consider the future of our own species. What does the study of interstellar objects tell us about the fate of civilization? If life has emerged elsewhere in the universe, has it also gone through the same stages of development that we have? Has it reached the point where it can explore the stars, or has it long since disappeared? These are questions that remain unanswered, but they raise critical reflections about the future of humanity. Will we, too, eventually become a cosmic civilization, sending our own objects across the galaxy in search of answers? Or will we, like so many other species before us, fade into history, leaving behind only fragments of our existence? In many ways, the search for answers to these questions is as much about the future as it is about the present. The study of interstellar objects forces us to think beyond our immediate survival and consider the long-term future of humanity. We are on the precipice of an era of unprecedented exploration, with the potential to travel beyond our solar system and explore the stars. As we develop the technologies and capabilities to study interstellar objects, we are also laying the groundwork for humanity's future as an interstellar species. This future, while still distant, is one that offers hope, adventure, and the possibility of expanding our horizons in ways we can hardly imagine today. 3IATLAS in all its mystery serves as a symbol of the unknown, a reminder that the universe is full of surprises, and that our journey of discovery is just beginning. It calls us to look beyond the familiar, to question our assumptions, and to embrace the unknown. The universe, it seems, is far more complex and dynamic than we could have ever imagined, and objects like 3IATLAS are merely the first whispers of a much larger cosmic story. As we continue to study these interstellar visitors, we are not just unlocking the secrets of distant star systems, we are also learning more about ourselves, our origins, and the future that awaits us in the stars. As we move forward, the study of objects like 3IATLAS will continue to shape our understanding of the universe and our place within it. The questions it raises about the nature of life, intelligence, and our future in space will inspire generations to come, and in the process it will remind us of the most fundamental truth, that no matter how far we go or how much we learn, the universe is vast, mysterious, and full of endless possibilities. In the face of that boundless expanse, the only limit is the reach of our curiosity and the courage to explore the unknown. As the astronomical community continues to reflect on the encounter with 3IATLAS, it's clear that its passage through the solar system was a moment of profound significance. What began as a simple observation by an automated telescope in Chile in July 2025 became one of the most groundbreaking moments in modern astronomy, forever altering our understanding of interstellar objects, space exploration, and our place in the universe. The mysteries of 3IATLAS are far from solved, and as more data continues to trickle in, our understanding of this cosmic visitor will undoubtedly evolve. Yet even with so many questions still unanswered, one thing is certain: 3IATLAS has left an indelible mark on humanity's quest for knowledge. In many ways, 3IATLAS is the archetype of what we are now coming to realize is possible: a deeper exploration of the unknown. For years we have looked out into the universe, searching for answers to questions that have long been on the edges of our curiosity. Who are we? Are we alone? What is the true nature of the cosmos? For much of human history, these questions were the stuff of philosophy, religion, and science fiction. Yet, with each new discovery, we have edged closer to answers that could one day define the human experience in ways we cannot yet comprehend. 3IATLAS, like the discovery of the first interstellar object, Oumuamua, has brought those questions into sharper focus. Before 3IATLAS, the concept of interstellar objects was largely theoretical, a notion explored in the works of astronomers and astrophysicists, but never something we thought we would encounter directly. Interstellar objects were considered the stuff of distant galaxies or hypothetical travelers through the void. But as 3IATLAS zipped past Earth, traveling at breakneck speeds from the depths of interstellar space, it became something more than just a scientific curiosity. It became a living, breathing reminder that we are not alone in the universe, at least not in the way we once thought. There are, after all, cosmic wanderers like 3IATLAS, roaming through space on their way to destinations unknown. They are the relics of other star systems, time capsules carrying the memories of stars that are no longer visible to us. The discovery of 3IATLAS brought us face to face with the reality that our solar system is not an isolated system of planets, moons, and comets, but a small part of a much larger cosmic web, one that stretches across vast distances and is filled with objects that tell stories far beyond our own experience. What's more, 3IATLAS is not the last of its kind. We can expect more interstellar objects to come, just as we've seen Oumuamua, Borisov, and now Atlas itself. With each new discovery, we will have a clearer understanding of the diversity of the universe around us, including the possibility of extraterrestrial life, the dynamics of planetary systems, and the processes of cosmic evolution. And while each of these objects is unique, each one will carry with it the same fundamental mystery that we've encountered with 3IATLAS, a mystery that fuels human curiosity and pushes the boundaries of scientific discovery. One of the most important legacies of 3IATLAS's visit is the shift it represents in humanity's approach to space exploration. For decades, our focus has been primarily on our own solar system, sending probes to distant planets, exploring asteroids and comets, and attempting to unlock the secrets of our planetary neighbors. While these missions have been tremendously successful, the discovery of interstellar objects has turned our gaze outward, toward the stars and beyond. The study of 3IATLAS reminds us that space exploration is not just about understanding the neighborhood we live in, but about exploring the vast, interconnected expanse that exists beyond. The very idea that objects from other star systems can enter our solar system and offer us glimpses into their distant past forces us to think of space as something much more dynamic than we previously imagined. As we develop the technologies and strategies needed to study more interstellar objects, we are laying the groundwork for a new era in space exploration, one that looks beyond the confines of our solar system, to the infinite possibilities that exist across the galaxy. The detection of 3IATLAS and its follow-up observations suggest that we are on the verge of an entirely new frontier in space science. Whether we are studying the formation of planets in distant star systems, tracking the trajectories of interstellar wanderers, or even one day sending spacecraft to intercept these objects, we are now equipped to expand our exploration into realms that were once considered unreachable. The tools we develop to study these interstellar visitors will undoubtedly have broader applications, advancing our understanding of both the cosmos and the technological feats needed to explore it. Furthermore, the significance of 3IATLAS extends beyond the scientific realm. This visit raises deep philosophical and existential questions about the nature of our existence. What does it mean to be human in a universe so vast and full of mystery? The study of interstellar objects forces us to confront our place in the cosmos, pushing us to reflect on the impermanence of life and the potential for life elsewhere. 3IATLAS, like the discovery of exoplanets and the search for extraterrestrial life, reminds us that we are part of a much larger story, one that stretches back billions of years and reaches forward into a future that we are only beginning to imagine. As we continue to search for life beyond Earth, the discovery of interstellar objects like 3IATLAS opens up new avenues of research. Could these objects harbor traces of organic molecules, evidence of past life, or even relics of long-dead civilizations? While it is still too early to say whether 3IATLAS holds any clues to extraterrestrial life, the possibility that life may exist elsewhere and that it may have traveled across space carried by comets or asteroids is something that we can no longer ignore. Every new object we discover, every new piece of data we gather, brings us closer to answering the question of whether we are truly alone in the universe. And as our understanding of interstellar objects deepens, so too will our ability to search for and recognize the signs of life elsewhere in the galaxy. At the same time, the passage of 3IATLAS reminds us that there is much we still don't know. While we have made incredible strides in our understanding of the universe, the mysteries surrounding this interstellar object highlight the limits of our knowledge. Its unpredictable behavior, its strange composition, and its sudden appearance from the depths of space show us just how much there is left to discover. For every answer we uncover, there are countless more questions waiting to be asked. And this, perhaps, is the true gift of 3IATLAS, the reminder that there are infinite mysteries yet to be explored, and that the pursuit of knowledge will always be a journey without end. As we reflect on the legacy of 3IATLAS's visit, we are reminded of the power of curiosity and exploration. 3IATLAS's passage was a fleeting event, but it has left a lasting impression on the way we think about the universe. Its visit forces us to reimagine the very nature of space and time, and to consider the vastness and complexity of the cosmos in ways we never thought possible. The legacy of 3IATLAS is not just in the data it has provided or the discoveries it has prompted, but in the renewed sense of wonder it has inspired. As we look to the future, we know that this is just the beginning. The universe is full of surprises, and as we continue to explore it, we will uncover new mysteries, new wonders, and new answers to the age-old questions that have driven humanity's quest for knowledge. In the years to come, as more interstellar objects are discovered and studied, the legacy of 3IATLAS will live on. It has shown us that the universe is more interconnected and dynamic than we ever imagined, and that the journey of discovery is only just beginning. Whether we are looking for life on distant planets, studying the formation of stars, or developing the technologies to send humans beyond our solar system, we will always be guided by the lessons learned from 3IATLAS, that the universe is vast, full of mysteries, and waiting to be explored. As we come to the end of our exploration of 3IATLAS, it becomes abundantly clear that this cosmic visitor has changed the way we think about the universe and our place within it. What began as a fleeting glimpse of a mysterious interstellar object has blossomed into one of the most significant chapters in the story of human exploration. The unexpected arrival of 3IATLAS in 2025 marked a turning point in our understanding of the cosmos, compelling us to rethink everything we thought we knew about comets, interstellar objects, and our place in a vast, unknown universe. For years, we have searched for answers about the origins of life, the formation of galaxies, and the nature of distant worlds. Yet, even as we unlocked many of the secrets of our own solar system, we remained blind to the much larger, interconnected cosmos that stretches far beyond our immediate reach. 3IATLAS has forever changed that. The very discovery of 3IATLAS and the subsequent revelations about its strange chemistry, unusual trajectory, and baffling behavior serve as a testament to the power of human curiosity. It is a reminder of why we look to the stars, not only to answer scientific questions, but also to engage in the age-old pursuit of understanding our existence. 3IATLAS's passage reminded us that there are mysteries waiting to be uncovered, and that space exploration is far from a finished endeavor. Its visit illuminated the universe's vastness, complexity, and at times the deep unpredictability of cosmic forces. However, in its unpredictability, it also demonstrated the tremendous potential for scientific discovery that lies in the unknown. In many ways, the legacy of 3IATLAS is rooted in the questions it raises. It has forced scientists and the public alike to confront some of the biggest and most profound questions we've ever asked. What is the origin of objects like this? What else is out there beyond the known boundaries of our solar system? And perhaps most importantly, are we alone in the universe? While we may not have all the answers today, 3IATLAS has sparked a new wave of curiosity and exploration, reigniting interest in the study of interstellar objects and the broader universe. It is now evident that we are only beginning to scratch the surface of what is possible in space exploration. The search for answers will continue, driven by the scientific community's relentless desire to unravel the mysteries of space and our own origin. Yet, the questions raised by 3IATLAS are not confined to the realm of science. The passage of an interstellar object through our solar system brings with it a broader, more existential reflection on humanity's place in the cosmos. 3IATLAS, as an emissary from a distant star system, forces us to consider the larger picture, the infinite nature of space, and the fleeting moment of our existence within it. As we examine the vast distances traveled by 3IATLAS, the millions or billions of years it has spent journeying through the emptiness between stars, we are reminded of our own temporal nature. The universe is, in many ways, indifferent to our existence. We are but a brief flicker in the grand timeline of the cosmos, one small moment in an eternal expanse. Yet, in our brief moment, we have made profound strides in exploring the universe, pushing the boundaries of what we can know and achieve. It is easy to be humbled by this realization, but it is also a call to action. In the face of such vastness, we are reminded that the pursuit of knowledge is not only an intellectual endeavor, it is a deeply human one. It is a quest that binds us together, transcending national borders, cultures, and even species. The discovery of 3IATLAS has provided us with a unique opportunity to reflect on who we are, why we explore, and what drives us to look up at the stars and seek the answers to life's greatest question. In that sense, 3IATLAS has served as a catalyst, rekindling the spark of curiosity that lies within us all. But 3IATLAS also forces us to think about the future. We are living in a pivotal moment in the history of space exploration. In the coming decades, new technologies, new telescopes, and more ambitious missions will allow us to continue the search for interstellar objects and explore the unknown corners of the galaxy. The discoveries made from studying objects like 3IATLAS will inform the next generation of space exploration, offering insights into how we might one day venture beyond our solar system. We are on the verge of building spacecraft capable of reaching distant stars, and missions designed to study interstellar objects up close are no longer the stuff of science fiction. They are the next frontier in human exploration. Yet, while space exploration is a technical and scientific pursuit, it is also a deeply philosophical one. As we expand our reach into the stars, we are forced to confront questions that have long been the domain of philosophy and existential reflection. What does it mean to be human in a vast and seemingly indifferent universe? What is the purpose of our existence in a universe so full of mystery? And what responsibility do we have in exploring this vast unknown? These questions are not new, but the discovery of interstellar objects like 3IATLAS forces us to think about them in a new context. As we continue to reach further into space, these questions will only become more pressing, reminding us that the answers we seek are not always found in data and facts, but in the very act of exploration itself. In the end, the legacy of 3IATLAS is not just about the specific scientific discoveries it has brought us, but about the larger message it carries. It is a reminder that the universe is full of surprises, full of mysteries, and full of beauty. 3IATLAS may have been an object of scientific study, but it is also a symbol of the curiosity, determination, and wonder that drive us to explore the unknown. Its visit to our solar system was brief, but it has left a lasting impression on our understanding of the cosmos and our place within it. It serves as a testament to the power of exploration and the drive to seek out the unknown. As we look to the future, the lessons learned from studying 3IATLAS will guide us in our ongoing journey to understand the universe, and in doing so, understand ourselves. As we continue to push the boundaries of space exploration, we will look back on 3IATLAS as the first of many interstellar visitors to pass through our solar system, each one offering new clues about the broader universe. And with each new discovery, we will be reminded that the pursuit of knowledge is never truly complete. There will always be new questions to ask, new frontiers to explore, and new mysteries to unravel. But it is this pursuit, this eternal drive to explore, that defines us as a species. The legacy of 3IATLAS and the discoveries that lie ahead will continue to inspire generations of scientists, philosophers, and explorers to look to the stars and seek out the answers to life's greatest questions. In that sense, 3IATLAS is not just an object in space, it is a symbol of humanity's unyielding curiosity, our drive to explore, and our eternal quest for knowledge. And as we continue our journey of discovery, we can be certain that the mysteries of the universe will always be waiting for us to uncover, one interstellar visitor at a time. In conclusion, the brief but momentous visit of 3IATLAS has marked a transformative chapter in humanity's ongoing journey of discovery. From the moment this interstellar traveler was detected, it sparked a chain of questions, insights, and reflections that are reshaping our understanding of the universe and our place within it. While 3IATLAS itself is an object of immense scientific interest, its impact extends far beyond the data we have gathered. It has challenged long-standing assumptions, deepened our curiosity, and opened up new possibilities for space exploration, all while forcing us to confront existential questions about the nature of life, intelligence, and the cosmos. For scientists, 3IATLAS is a window into the vast and largely unexplored realm of interstellar space. Its unexpected composition, strange trajectory, and anomalous behavior have led to a re-evaluation of the very foundations of celestial mechanics, chemistry, and astrophysics. Objects like 3IATLAS, which come from distant star systems, having traveled across interstellar space for eons, offer unique insights into the conditions that exist beyond our solar system. The fact that we are now able to observe and study such objects brings us closer to understanding the building blocks of the universe, the formation of planets, and the potential for life beyond Earth. As 3IATLAS's passage has proven, there are cosmic wonders waiting for us to uncover, and the tools to study these interstellar visitors are just beginning to be developed. This encounter has highlighted the need for new technologies and approaches in space exploration. From more advanced telescopes capable of tracking fast-moving interstellar objects to spacecraft that might one day assist these visitors, 3IATLAS's passage underscores the urgency of expanding our capabilities. As the field of interstellar object research grows, humanity is on the cusp of a new frontier in space exploration. The tools we develop now to understand these objects will have far-reaching applications, not only for studying comets, asteroids, and planets, but also for exploring distant star systems and perhaps even reaching them in the future. Yet, the significance of 3IATLAS is not just in the hard data it provides. Its arrival forces us to reckon with larger, more philosophical questions. In a universe that stretches over billions of years and vast distances, we are reminded of the ephemeral nature of our existence. 3IATLAS's long journey through the cosmos, crossing the void between stars, is a humbling reminder of how small we are in the grand timeline of the universe. But rather than invoking despair, this realization invites a sense of wonder and urgency. The mysteries of the cosmos are vast and often elusive, but the very fact that we can observe and study these distant objects speaks to humanity's potential for discovery, exploration, and understanding. Moreover, 3IATLAS challenges our understanding of life itself. The idea that objects like this could carry remnants of other star systems, possibly even the building blocks of life, is a tantalizing possibility that raises the stakes of our search for extraterrestrial intelligence. While we may not yet have answers, 3IATLAS's visit strengthens the belief that life, or at least the ingredients for life, could be widespread in the universe. This realization deepens our understanding of what constitutes life, intelligence, and the processes that give rise to both. As we look to the future, 3IATLAS represents both a milestone and a beginning. It has proven that the universe is far more interconnected than we previously thought, that our solar system is just one small part of an infinitely larger cosmos. The path ahead will be one of constant discovery, fueled by the technologies we are developing today and the questions we continue to ask. We are no longer limited by the boundaries of our solar system. As we develop the tools to track and study interstellar objects like 3IATLAS, we will expand our horizons, learn more about the stars and systems that lie beyond us, and perhaps unlock the secrets to the origin of life itself. Ultimately, the legacy of 3IATLAS lies not just in the scientific advances it has inspired, but in the way it has reignited humanity's curiosity and sense of purpose. It reminds us of the infinite possibilities that await as we venture further into the cosmos, and it calls us to continue asking the fundamental questions: what is the universe made of? How did it all begin? Are we truly alone, or are we just one small part of a much larger story? The pursuit of answers to these questions will define the future of space exploration, and perhaps humanity itself. 3IATLAS has opened a door to the unknown, and as we walk through it, we are bound to discover even more about the universe and about ourselves. The future of space exploration is one that promises to be as awe-inspiring as the journey that 3IATLAS has begun. This encounter is only the first of many, and as we continue our search for answers, we will find ourselves looking up at the stars with renewed wonder and anticipation, ready to learn, explore, and understand the cosmos in ways we never thought possible.